So our second lecture in chapter 20 on thermodynamics deals with the concept of Gibbs free energy. So conceptually, we're going to be talking about how you predict spontaneity, and we're going to kind of have a win-lose philosophy that will talk about the different contributions that we can have from entropy and enthalpy. Remember, in our last lecture, we talked about the fact that neither entropy nor enthalpy alone is sufficient to predict spontaneity, and it really is the combination of both of them. We'll close with a little bit of a qualitative discussion on how temperature affects spontaneity, and that's going to then lead into our last lecture on thinking about quantitatively how we can determine how temperature affects spontaneity. So from a skills standpoint, we'll learn two ways to calculate delta G. One is using enthalpy and entropy parameters, and then the other is using Appendix B. And then we'll wrap up with a couple qualitative problems thinking about the effect of temperature on spontaneity. So a really important equation, really important slide here. Not an equation you'll need to memorize, one will be that will be provided, but it allows us to see how enthalpy and entropy both contribute to spontaneity or free energy. So with this equation, these are letters that you need to make sure that you know that free energy is G, and that has to do with spontaneity. Enthalpy is H, and that has to do with heat, and I want you to think about bonds and intermolecular forces. S has to do with entropy, so think about disorder and that phrase, more molecules moving more. And then obviously T has always been temperature for us. So again, this really important equation allows us to see that both enthalpy and entropy contribute to free energy. Another thing that's important to kind of make sure that you remember is a spontaneous reaction is going to be one where delta G is negative. If delta G is positive, we classify that reaction as non-spontaneous. And then if delta G happens to be equal to 0, we'd say that process is at equilibrium. And this is going to be a really important piece because that's going to allow us to tie this chapter with previous chapters on discussing equilibrium. So remember when we had our free energy diagrams and we talked about the idea of whether and how much? Well, the sign of delta G is again whether a reaction happens. Reactions like to go downhill, and negative delta G means that reaction goes downhill. And then as we'll learn in our very last lecture here, the magnitude of delta G tells us how spontaneous it is. How much are we going downhill? And again, we know that that relates to how much product we make. So a really important slide here to kind of tie this all together. Well, in the beginning, I told you there's going to be two ways that we'll learn how to calculate delta G. The first is going to be calculating delta G using what we call the Gibbs free energy equation. So if we have the enthalpy and the entropy for a process, we can use those to determine the free energy. So what we're going to do is use enthalpy and entropy values that we get from Appendix B, and then we'll use those to calculate delta G. So here's our first problem. Again, the prompt just gives us a little bit of background here on thinking about what we're going to have for this chemical reaction, which is a disproportionation reaction. But all we really need to know is here's our balanced chemical equation. Go ahead and use Appendix B to calculate enthalpy and entropy values for this equation, and then use our gold standard Gibbs free energy equation here to calculate delta G. So why don't you guys go ahead and pause the video and try to work through this solution. Now I know there's a lot on this slide here, but let's just take it apart piece by piece. Here is the main money equation that we're going to have here for calculating delta G. We need to calculate delta H and delta S using values from Appendix B. So that's what we've got down here. Here's our balanced chemical equation, and we're just pulling these numbers off of Appendix B. Some things to make sure we keep track of is the fact that the units of delta H are going to be kilojoules per mole. For entropy are going to be joules per mole Kelvin. So we have to make sure that we reconcile the fact that these two units come or enthalpy and entropy come in different joule units. One's kilojoules, one's joules. And we need to make sure if we're talking about temperature, we always convert to Kelvin. So I'm not going to go through the details for how we solve this process or solve for enthalpy and entropy here. Remember, it's products minus reactants. Our gains in our process minus our costs. But at the end of the day, we see that this process is an exothermic reaction. But unfortunately, the entropy of the system is unfavorable. It happens to be negative. Remember, entropy, if it's favorable, is going to be positive. Okay, so again, unfavorable entropy, but it's a reaction that gives off heat. It's exothermic, so that's favorable. What we're going to do now is show that you could get the same answer, at least with an experimental or rounding error, using Appendix B to calculate delta G. So I'm not going to give too much of a prompt for this problem, but see if you can pull the same values for these species from Appendix B, but now using the delta G column. Pause the video and go ahead and try and solve those problems. All right, pretty straightforward problem here. You're literally just grabbing these same values where on the previous problem you went to the left to grab the enthalpy and the right to grab the entropy. You're just grabbing that middle column of values. Same thing, products minus reactants, making sure to scale up for corresponding coefficients if they're non-unity. And we end up getting, within experimental or rounding errors, the same value for delta G. So this is a spontaneous reaction. Spontaneous because delta G is negative. Okay, so again, thinking about this important gold standard equation, what we're going to do now is a little sort of math exercise. Remembering, if we want something to be a spontaneous reaction, delta G must be negative. So let's think about the different mathematical permutations that we could put in here. Well, if delta G is negative, like if we have an exothermic reaction, that's certainly going to help my left side of the equation be negative here. Similarly, if delta S is positive, that means I'm going to be subtracting something off of what was already a negative number. So I'm just going to make it even more negative. So if we want to think about whether or not something's spontaneous, an exothermic reaction that has favorable entropy is going to be sort of a win-win situation. So the next 4 slides are going to kind of walk us through the different permutations of winning and losing. So if a reaction is going to be always spontaneous at any temperature, let's just see if we can reason our way through what kinds of values we'd like to have for enthalpy and entropy. Okay, so we just said if delta H is negative, that's going to be sort of a favorable process. So we want delta H to be negative, and if delta H is negative, that's an exothermic reaction. Again, if we want to make delta G negative, we want delta H to be negative. We want delta G to be negative. We want delta H to be negative, and we want delta S to be positive. That mathematically will never be a negative number, right? If we've got a negative number here and we're subtracting something off of it that's positive, we're only going to be making it more negative. Remembering, of course, that temperature will always be a positive value if it's in Kelvin. So again, in this situation, we have an exothermic reaction, okay? And we can see here that entropy is positive. Entropy is favorable. So this is a win-win sort of situation. This is a win-win situation. So being a win-win situation, that's going to be favorable and spontaneous all the time. Now, one of the things to kind of highlight here is we could predict some of this from our chemical equation. We can't necessarily predict the exothermicity of it. We couldn't have predicted unless we were measuring something there. But just looking at this chemical reaction, we generate more molecules that are moving more because they're gases. So we would have predicted that entropy would be favorable for this. All right, let's take the lose-lose situation and see if we can kind of walk our way through the fact that this is lose-lose. A lose-lose situation is never going to be spontaneous no matter what temperature you have it at. Well, if that's the case, we'd start out by having delta H be positive, which means the reaction is endothermic. And again, if the entropy is negative, that means that we would be subtracting off a negative number, which really means we're adding something positive to something that was already positive. There's no way mathematically that we would end up with delta G being anything else than positive. So this reaction is never going to be spontaneous. Again, there's not really an easy way to look at a chemical reaction and predict the enthalpy of it, but we can predict entropy. Looking at this situation, right, we have 3 moles of gas that become 2 moles of gas. In the whole more molecules moving more situation, this is actually fewer molecules. So this is unfavorable entropy, and unfavorable entropy is negative. So we can see that here, and coupled with an endothermic reaction, this process will never be spontaneous at any temperature. All right, so we've got a win-win combo and a lose-lose combo. What about the two win-lose combos? All right, so the win-lose combos have a temperature dependence. So let's see if we can walk through kind of the process here, the thought process for this, right? In this case, we have an endothermic reaction, so enthalpy is not being helpful to our spontaneity, but we do have a process that has favorable entropy. So again, this is unfavorable. So this is again our lose, and this is favorable. This is a win. So in this case, and again, this is something we could have predicted looking at what we have here. Again, we've got favorable entropy. We've got 3 moles of gas over here becoming 4 moles of gas. So that's going to be favorable. So in this case, if we look at this mathematically, we have something that is a lose situation here, and we're going to be subtracting off something that is a win. Mathematically, we want to make this be the largest number possible. We want to have this number be helping us because that's our winning piece. So in that case, increasing the temperature is going to help this reaction because we make it more significant from a mathematical standpoint. All right, one more permutation. This is again another win-lose combination, but this time our enthalpy happens to be winning, but our entropy is losing. Because in this situation, our entropy is something that we want to diminish its contribution for because it's a losing component, we actually want to decrease the temperature to make this reaction more spontaneous or more favorable. And again, looking at what's happening here, we actually have unfavorable entropy in that we ask 3 moles of a gas to basically all be sitting still in a solid. So we could have predicted that the entropy would be unfavorable from this reaction. All right, so all of those examples on those previous 4 slides are basically the different permutations that we have here in this table. So again, I have here that you could memorize this table if you want, but I think it's a lot easier to understand it. We just went through all the permutations and hopefully they make sense. Again, having a situation that's always spontaneous, never spontaneous, or again, the 2 temperature-dependent situations. And because entropy is the component that's dependent on temperature, if we have entropy that's helping us, we want to increase its contribution, so we're going to have a higher temperature. See how temperature multiplies by entropy here? Again, if entropy is not helping us, we want to diminish its contribution mathematically, so we want to decrease temperature to make that number numerically smaller. All right, so 2 last problems here to wrap up what we have in this lecture here. The first is a molecular scenes problem. So I'll set up the problem for you and we'll have you think about it. So again, the following scenes represent a phase change for water. So each of these represents a water molecule. So see if you can think about and name the phase change that's going on, and then think about the signs of enthalpy and entropy for this process, and then predict which of those 4 situations we're going to have. Is it always spontaneous, never spontaneous, or spontaneous at either low or high temperatures? So go ahead and pause the video and see if you might be able to walk through this thought exercise, thinking about enthalpy, entropy, and free energy. All right, so hopefully everybody's good recognizing that this is a condensation reaction. We're taking water that was in a gas phase and having it solidify, or I shouldn't say solidify, condense into a liquid phase. What might not be obvious to see is that this is going to be an exothermic process. Heat is released. If you're ever confused about a process, see about moving it in the reverse direction. If I had liquid water and I wanted to make it into gaseous water, yep, heat would have to be over on this side. Okay, so this is an exothermic process. We actually need to remove heat and energy from our system in order to get those gaseous water molecules to condense into the liquid phase. So because we know that it's an exothermic process, we know that delta H is negative. That's a winning situation. So if we think about what happens for entropy, entropy here is going to be unfavorable. We have gaseous water that's being forced to sit still as a liquid. So in our whole more molecules moving more philosophy, these molecules are moving less. So that's unfavorable from an entropy standpoint. Because we don't have a win-win or a lose-lose situation, we can cross off these two pieces. It's not going to be spontaneous at any temperature, and it's not going to be spontaneous at no temperature. So now we have to think about which of the temperature situations is going to be more favorable. All right, so because we know that entropy is unfavorable, we want to diminish its contributions, which means we diminish the temperature. We lower the temperature. All right, so we went through this problem just using the math and the equations to think about it, but you can actually walk through this problem logically. Think about this. If you wanted to have, let's say, water vapor in the air condense on a glass, would you want that glass to be a cold glass of iced tea or a hot cup of coffee? Obviously, an iced tea is going to condense more water on its outside than you would with a hot cup of coffee. So again, just another example of kind of putting a real example into place here. All right, last problem that we have here. Again, just showing us a chemical reaction. We don't really need to understand the context for what's going on, but they give us some pieces of information here. They actually give us free energy, enthalpy, and entropy for this process. So the questions ask us, is it spontaneous? How will delta G change if we were to increase the temperature? And if we assume that enthalpy and entropy are constant with temperature, that means that there's actually not a phase change that's occurring in this process. Is the reaction spontaneous if we heat it all the way up to 900? So try pausing the video and seeing if you could work through the answers to these questions. All right, A is pretty straightforward. If you want to answer the question, is a reaction spontaneous, you just need to look at the sign of delta G. Sign of delta G is negative, so that reaction is spontaneous. If we want to think about the temperature dependence of delta G, we need to look at the entropy. In this case, the entropy is a losing parameter in this system. So if we increase the temperature, that actually makes that losing contribution be more significant. So delta G will actually become more and more positive, becoming less and less spontaneous. So the last piece actually has us use our gold standard Gibbs free energy equation. And since delta H and delta S are going to be constant with temperature, we can put these same two values in, and we can just change the temperature, making sure we change it to Kelvin. So again, here's our delta H parameter. Here's our delta S parameter converted to kilojoules here. And then we need to convert our temperature to Kelvin to make sure to cancel out the units of Kelvin there. We see that delta G now becomes positive 22 kilojoules. Makes sense. We knew that as we increase the temperature, delta G would go from a negative number to becoming more and more positive until it eventually became 22 kilojoules at 900 degrees C. So one of the things that we'll move on to in our next lecture is just to say, well, okay, as we increase temperature, this became more and more positive until eventually it became 0. And then it continued to increase. So at 900 degrees C, it became 22. Well, at what temperature did it actually make that change? We're going to call that temperature the pivot point. And we'll learn in our next lecture how we actually solve for the answer for that question. All right, not a lot to summarize from this lecture. Again, Gibbs free energy allowed us to use two equations to actually calculate its value. We could use Appendix B and kind of our gold standard kind of way of using delta or Appendix B values, or we learned a new important equation that highlights the importance of both enthalpy and entropy to contribute to free energy. Again, reminding us of the temperature dependence of entropy. We went through kind of a couple of problems here to both predict using a molecular scene the contributions of enthalpy and entropy to a process, and then starting to do some calculating of those contributions. So we'll move on in our next lecture to expand on this principle a little bit further.